Welcome back to the deep dive. Today we're doing something a little bit different.
Yeah, quite different.
Usually we take a look at a finished product, right?
Yeah.
A new strategy, a historical event, something that's already wrapped up with a nice bow.
Safe and sound.
Exactly.
Hmm.
But today we're looking at a crisis. And I really don't use that word lightly here. We're looking at a massive structural panic happening inside the boardrooms of the world's biggest car manufacturers right this second.
It is a crisis of survival, really. If you look at
Right.
the sheer panic in the eyes of, a legacy automaker executive, when you mention software integration, you'll know exactly what the report is talking about. It's the defining anxiety of the decade for this industry.
Right, so we are analyzing a strategic report covering the global automotive landscape for 2024 through 2026. And the headline, the big hook here is this concept of zero prototypes.
Which sounds completely made up.
It does. When I first saw that title, I admit my skepticism radar went off. It sounds like marketing fluff. Zero prototypes. It implies they're going to stop building test cars entirely.
Yeah, it sounds like a tech startup pitch, not how you build a Ford or a Mercedes.
Exactly. It sounds impossible because, I mean, we've spent 100 years building cars the exact same way. You design it on paper, or well, CAD these days. You build a mule physical prototype, you drive it into a wall, you drive it on a frozen lake, and when it breaks, you fix it.
Rinse and repeat. The classic build, break, fix loop.
Yeah, that linear loop.
Yeah.
But the report makes it very clear that this loop is dead.
It's completely dead because it takes time. You build the mule, you wait 3 months for the parts, you test it, you find a problem, you re-engineer it, and then you have to build another mule.
Which is incredibly expensive.
It is. But right now, the car industry doesn't even have the time to care about the expense. The report we're diving into today aggregates data from heavy hitters like VI Grade, AVL, and Ford. And the central argument is that if you are still building physical prototypes to validate your software in 2026, you're already dead.
You just don't know yet.
Right. Because
Yeah.
the car isn't just a car anymore.
It's a software-defined vehicle, the SDV. We hear that acronym thrown around constantly in these reports. But what does it actually mean for, say, the guy welding the chassis on the factory floor?
Well, SDV is the buzzword, but let's unpack what it actually means for the engineering process. A modern luxury EV has more lines of code than a fighter jet.
Which is an insane statistic to just casually throw out there.
It is, but it's true. It has centralized compute, zonal controllers, cloud connectivity. If you try to validate all that software by putting a human driver in a physical car and telling them to, go drive around and see if the screen bugs out,
He'd go bankrupt.
you'd go completely bankrupt. The math simply doesn't work. The complexity of the software has totally outpaced the physical world's ability to test it.
So this whole zero prototypes thing isn't just some aspiration, it's an absolute necessity.
It's a survival mechanism to deal with complexity. They call the ultimate goal virtual sign-off.
Virtual sign-off.
Yeah. They want to reach a point where a senior executive can sit in a simulator, drive a car that doesn't literally exist yet, and sign a legal document saying, yes, this is safe to put into mass production, without ever touching a piece of real steel.
See, that is a terrifying amount of trust to place in a computer simulation.
Mm-hmm.
I mean, we've all played video games where the physics glitch out and the car suddenly flies into outer space. You're telling me they're betting trillion-dollar companies on this?
It's a massive bet. And that is exactly why this deep dive is going to be about the technology required to earn that trust. We aren't just talking about better graphics on a screen.
Right, the report goes way beyond that.
Way beyond. We're talking about simulators that trick your inner ear. We're talking about AI that hunts for failure modes that humans literally can't imagine, and a complete restructuring of the global supply chain.
Okay, let's get into the first section of the report. They call it the paradigm shift, this transition from the test mule to the virtual sign-off. Now, you mentioned that the linear way of doing things is dead, but surely they still build some physical cars, right?
They do, yes, but the ratio is completely flipping. The report highlights a major target across the industry, which is reducing physical prototype counts by 40%.
40%. That is a massive number when you consider that a single prototype, like a hand-built mule, can cost hundreds of thousands, sometimes millions of dollars.
It's huge money, but again, it's also about the speed. They are talking about doubling the speed of development, 2x, cutting the whole cycle from 4 years down to 2 years.
Because if you're a legacy automaker and a company like NIO or Tesla is putting out a radically updated model every 18 months, You just cannot afford a 48-month development cycle.
You'd be obsolete by the time your car hits the lot.
So virtual sign-off is the holy grail here.
Mhm.
But how do you actually get a veteran engineer to trust it? The report lays out 3 pillars for this strategy. Let's break those down for everyone listening. The first one is validation reformatting.
Which I know sounds like terrible corporate speak.
It really does. Validation reformatting.
But it's actually the hardest part of the whole shift because it's purely cultural. It's about changing the business process. Currently, most legacy car companies have a rigid rulebook that says you cannot launch this vehicle until it has been driven 1 million physical miles.
Right.
Validation reformatting means tearing up that rulebook and writing a new one that says you cannot launch until the car has been driven 10 million virtual miles and passed these highly specific digital edge case tests.
So it's literally moving the official stamp of approval from the physical test track over to the server farm.
Precisely. And then the second pillar is the one that really bridges the gap for the skeptics. They call it digitizing sensory experience.
And this is where we get into the feel of the car. Because, look, I can totally understand testing a door latch on a computer.
Yeah.
You run the physics, it clicks or it doesn't. But driving is emotional, it's visceral. How do you digitize that feeling for a test driver?
You have to capture what the report calls the full spectrum. They talk about capturing everything from 0 to 20,000 hertz.
0 to 20 kilohertz, which is the full range of human hearing.
Hearing and feeling, and this distinction is really vital. 0 to 20 hertz is what engineers call whole body motion.
Okay.
That's the sway of the car when you take a sharp turn. It's the heave when you go over a steep hill.
Yeah.
You feel that deeply in your vestibular system, in your gut.
Those are the motion sickness frequencies, basically.
Exactly. Then you move up to 20 to 200 hertz. That is tactile vibration. That's the steering wheel shaking just a little bit when you go over rough, broken pavement. That's the seat buzzing from the engine.
Got it.
And then from 200 all the way up to 20,000 hertz, that is pure audio. Wind noise hitting the windshield, the electric motor whine, the tire roar. If you want a veteran test driver to sign off on a car virtually, they need to feel and hear all of those frequencies synchronized perfectly.
Which sounds incredibly difficult to pull off.
And that brings us to the third pillar.
Boundary dissolution.
Yeah.
This is blending the lines between the physical test track and the computer lab. They're using mixed reality XR and massive cloud collaboration. Give me an example of how that works in practice.
Imagine a test driver sitting in a simulator rig in Germany. But the car they are currently driving is actually a live software model being tweaked and recompiled by an engineer sitting in Detroit.
So the engineer in Detroit changes the code for the suspension stiffness, and the driver in the simulator in Germany feels that change instantly.
Instantly, it completely dissolves the barrier between the act of designing and the act of testing. In the old days, those were two entirely different departments that barely spoke to each other. Now they were in the exact same loop.
Which brings us to the human-centric loop section of the report. It emphasizes that this whole transition isn't just about automation. It's not about letting robots design our cars.
No, and that is a critical distinction to make. There's a lot of fear out there that AI is just taking over the entire design process. But this strategy argues the exact opposite. It's about putting the human back in the loop, but much, much earlier.
Right, because usually the test driver only gives their feedback at the very end of the line, right? When the physical prototype is finally built.
Exactly. And by then, the expensive steel molds are already cut. It is way too late and way too expensive to fix anything major.
So the driver says, hey, the steering feels totally numb, and the executives say, too bad, we launch in 3 weeks, ship it.
That's exactly how bad cars get made. But with these high-end simulators, the test driver, the CEO, the lead chassis engineer, they can all drive the concept car on day one. The report calls it same-day design, same-day experience. You code it in the morning, you drive it in the afternoon.
Okay, let's get into the hardware then. Because if I am that executive and I'm supposed to sign off on a billion-dollar vehicle program based on a simulator ride, that simulator better be absolutely perfect.
It has to be flawless.
I've been in flight simulators before. You know, the big hydraulic hexapods at museums or training centers, they jerk you around, you feel the bumps. Is that the kind of machinery we were talking about here?
No, those are basically dinosaurs compared to what we are seeing in this 2024 to 2026 window. The report focuses heavily on a complete shift in simulator architecture. The old school method, like those flight sims you mentioned, uses hydraulics or geared electric motors.
Okay, stick with the gears for a second. Why are gears a problem for car simulation?
Think about how a gear works. You have metal teeth meshing with other metal teeth. When you change direction, say, from a hard left turn to a hard right turn, there is a tiny microscopic moment of slop or backlash where the teeth aren't actually touching,
Right.
and then they slam back together to catch the new direction. That creates a tiny vibration. It creates a mechanical noise.
Friction.
Parasitic friction is the technical term they use. Now, in the old days, if you were testing a Ford Mustang with a roaring V8 engine, the engine was so loud and the whole car vibrated so much that you wouldn't even notice if the simulator rig hummed or clicked a little bit. The physical car masked the simulator's flaws.
But now we are driving electric cars.
And an EV is essentially a silent acoustic chamber. If you are sitting in a virtual Porsche Taycan, and it is dead silent inside, and you turn the wheel, and the massive simulator underneath you goes, "Work, look,"
The illusion is completely broken.
immediately. You cannot test the car's NVH noise, vibration, and harshness because the simulator itself is polluting the data with its own noise.
So how do they fix it? The report highlights a specific tech here called Hexarev.
Right, Hexarev, which utilizes a direct drive architecture. So imagine a massive floating platform. Instead of gears or rubber belts pushing it around, it is floating on magnetic fields controlled by massive electrical coils.
Just like a maglev train.
Sort of. It's essentially a giant speaker voice coil, but big enough and powerful enough to hold an entire car cockpit and a human inside it.
So there's absolutely no physical contact, no
Roosh.
grinding gears.
Precisely. Because it is a magnetic direct drive system, it has zero backlash, it is dead silent. But more importantly, it has incredible bandwidth. We need to go back to those frequencies we talked about earlier.
The 0 to 20 kilohertz range.
Yes. Most of the old flight simulators are really only good at the low frequencies, 0 to 20 hertz. That's the heavy stuff. The body roll when you corner, the pitch when you brake. But the actual texture of a car lives in the higher frequencies.
What do you mean by texture?
20 to 200 hertz is the road boom. It's the literal sound and feel of the rubber tires slapping against the pavement. 200 to 2000 hertz is the electric motor whine spinning up.
And this direct drive system can actually replicate that tiny stuff.
It can vibrate the entire multi-ton platform at those exact microfrequencies. So when you drive over virtual cobblestones in the simulation, you don't just see them on the screen. The chassis of the simulator vibrates with that specific high-frequency rattle. Your body physically feels the texture of the road.
Wow.
That is the digitizing sensory experience pillar in action. If you don't have that high-frequency fidelity, the test driver simply cannot evaluate the ride quality.
It sounds like high-fidelity home audio, but for your entire body.
That is a perfect analogy. It is haptic high fidelity, and it's combined with what the industry calls the hyperdock. This is fascinating. They embed active belts and seat shakers directly into the driver's seat that are synchronized perfectly with the main magnetic platform.
Okay.
So if you hit a virtual pothole, the platform drops, that's the low frequency. The seat actively kicks you in the back, that's the mid frequency. And the spatial audio system plays the loud thud, the high frequency.
And if those three things don't happen at the exact same millisecond?
Your brain rejects it. And that leads us to the single biggest problem with simulators throughout history, the vomit factor.
Right, motion sickness.
Yeah.
I mean, even in really good consumer VR headsets, people get queasy after 20 minutes. If you are in a massive industrial simulator bouncing around for a 4-hour test shift,
Yeah.
how do they stop these drivers from just constantly getting sick?
Motion sickness in simulators is almost entirely caused by latency. It's a conflict between what your eyes see and what your inner ear feels. Your eyes see the sharp turn coming up on the screen. Your brain instantly expects your body to feel the lateral G-force.
Makes sense.
If there is even a tiny delay, and we're talking milliseconds here, between seeing the turn and feeling the movement, your inner ear panics. It literally thinks you have been poisoned.
Wait, poisoned?
Biologically, yes. In nature, throughout human evolution, the only time your vision and your sense of balance disconnect like that is if you have eaten a toxic berry or a bad mushroom.
As wild.
So your body says, empty the stomach. Get the poison out right now. That is structurally why you throw up in a simulator.
It's a biological defense mechanism against bad latency. So how do they solve it?
The report details a breakthrough called zero latency AI compensation. And this is really clever engineering. They use machine learning algorithms that are pre-trained on the specific physics model of the car being tested. The AI literally predicts where the car is going to be in the next few milliseconds.
It predicts the future.
A very, very short-term future. It sends the movement signal to the motion platform before the physics engine has even finished calculating the visual frame for the screen. It moves the hardware early to compensate for the physical inertia of having to move heavy actuators.
So by the time your eyes actually see the turn on the screen, the heavy metal platform has already started moving to match it perfectly.
Correct. It tricks the vestibular system completely. The latency effectively drops to zero, or at least far below the threshold of human biological perception.
All right, so we have the body, the hardware. Let's talk about the brains of this operation, the cloud and the AI. The report mentions a framework called VI data drive. This seems to be more about logistics than physics.
It is. It's about breaking down the physical walls of the lab. Traditionally, a high-end simulator was a standalone island. You had a massive supercomputer sitting next to the rig, and the data stayed right there in that room. If you wanted to share a test run with a colleague in Japan, you literally had to copy files onto hard drives and ship them, or spend hours uploading massive datasets. It was slow.
And VI data drive moves the vehicle model and the simulation engine itself into the cloud.
Exactly. It means an engineer in Stuttgart can run a simulation on a new suspension setup, and a team in Detroit can review the telemetry of that drive instantly. It democratizes the data across the global company. But there is a massive risk here.
What's the risk?
With all this computing power, isn't there a risk of just over-testing? Like, if you can simulate literally anything, do you just run simulations 24/7?
The analysis paralysis problem.
They call it infinite validation in the report. If you try to test everything, you finish nothing. And this is where companies like AVL come in with something called active DOE. That stands for Design of Experiments.
Okay, active DOE. What does that actually mean in plain English for the listener?
It means using AI to hunt for the weird stuff. Instead of running a test like driving at 30 miles per hour and then running another test driving at 31 miles per hour, which is boring and totally predictable, the AI looks for nonlinear regions.
Nonlinear regions.
The edge cases. The exact moments where the vehicle system becomes unstable or unpredictable. Maybe it's braking hard on black ice while turning left with a low battery while the ABS is malfunctioning. The AI hunts for these breaking points automatically. It ignores the boring, normal driving stuff where it knows the car is safe and focuses computing power purely on where the car might fail.
So the AI is actively trying to break the car.
It is relentlessly trying to find where the car might break. The report says this specific AI approach reduces motor calibration time by 50%. And crucially, it allows for safety testing that you simply cannot do in the real world.
Give me an example of something you can't test in real life.
Battery thermal runaway.
Oh, wow.
Right. You cannot purposefully explode a massive lithium-ion battery pack in a physical prototype car with a human test driver inside just to see what happens to the software. It's highly unethical and incredibly dangerous. But in a virtual environment, you can trigger a catastrophic thermal runaway event safely. You can see, does the software correctly alert the driver? Does it automatically roll up the windows to block the smoke? Does it unlock the doors? Does it shut down the high voltage system in time? No one gets hurt and no expensive metal is wasted.
That is incredible. And that connects directly to what the report calls the big loop, right?
Yes, the big loop. This is the new cycle of life for automotive data. It starts with real car collection, gathering actual driving data from existing cars that are out on the road right now.
Right.
That real-world data goes up to the cloud to generate new simulation variants. Those variants are used to train a neural network. That neural network improves the vehicle software, which is then sent back down to the physical cars on the road via OTA, over-the-air updates.
So just to be clear, the physical car I drive to the grocery store today is gathering data to train the simulator that will design the software update my car gets tomorrow.
Exactly. Your physical car gets smarter over time because its digital twin is working overtime in the cloud.
Let's shift gears a bit to the experience inside the cabin. Because as we know, cars are basically just giant screens on wheels now. The HMI, the human-machine interface, is a huge competitive deal.
It is the main battlefield for consumers. If your screen lags or the menus are confusing, people will hate the car. It doesn't matter if it goes 0 to 60 in 3 seconds. The report highlights the use of mixed reality here, specifically using advanced headsets like the Vardo XR4.
I've actually heard of Varho. They make those ultra-high-resolution enterprise headsets that are basically indistinguishable from reality.
Right. They are incredible. So instead of building a physical dashboard out of clay and plastic and wiring it up, which costs thousands of dollars and takes weeks, they just put the driver in a basic seat with a physical steering wheel and real pedals, and then put the XR headset on.
Okay.
The dashboard, the infotainment screens, the climate control buttons, they're all totally virtual, projected into the headset.
But the wheel and the pedals are real.
Yes, so you have the necessary tactile feedback for actually driving the vehicle, but the visual interface is completely digital and can be changed in seconds. This is critical for testing things like level 3 autonomous driving.
The handover.
The handover. That terrifying moment when the car's computer says, I cannot handle this construction zone anymore, human. You need to take the wheel right now.
And you have, like, what, 3 seconds to figure out what is going on before you hit a wall?
Precisely. Testing that logic in a real car on a real highway is incredibly dangerous. What if the human doesn't wake up in time? What if they panic and swerve? In XR, you can test that exact handover scenario 1,000 times with different people.
You can see how they react.
You can see. Is the audio alert loud enough? Is the screen flashing the right shade of red? Does the steering wheel vibrate aggressively enough? You can tune that wake-up call until it is statistically perfect without risking a single real-world crash.
And visually, from what I'm reading here, they aren't using some clunky industrial CAD graphics anymore. The report talks heavily about Unreal Engine 5.
Yeah.
I mean, that is a video game engine.
It absolutely is. It's the exact same engine behind games like Fortnite and demos like The Matrix Awakens, but the auto industry is adopting it globally because of a feature called nanite technology.
Nanite.
It's a rendering technology that allows for billions of polygons to be rendered in real time without crashing the system. It basically means movie-quality visuals running live. But for cars, it's not just about making it look pretty for the human driver, it's actually about the virtual sensors.
What do you mean by that?
A modern car has an array of cameras that see the road to stay in the lane or brake for pedestrians. If you are testing that camera software in a simulator, the virtual world needs to look exactly perfectly like the real world.
Oh, I see.
Right. Light reflections on puddles, dynamic shadows from moving trees, lens glare from the setting sun. Unreal Engine 5 provides that photorealistic fidelity so the car's computer actually believes it is driving outside.
So the car's onboard computer is essentially playing an incredibly realistic video game, thinking it is real life.
That is a perfect way to put it, because if the shadows are rendered incorrectly in the game, the car's AI might get confused and brake for no reason in the real world.
Okay, we have covered the hardware and the visuals, which is definitely the sexy part of the report. But there is a section here called Correct by Design that I think is actually the most important part of this entire strategy. It deals with the invisible infrastructure, the code itself.
It is the most critical part, hands down. We are moving to what the industry calls zone architectures. In the past, a normal car had maybe 100 little separate computers, ECUs, one for the power windows, one for the engine timing, one for the airbags, and they didn't really talk to each other much.
They were completely isolated.
Right. But now we are consolidating. We are putting everything onto one or two massive central supercomputers. So the critical code that controls your anti-lock brakes is literally running on the exact same silicon chip as the code that runs your Spotify app or your heated seats.
Which sounds like an absolute recipe for disaster. What if the heated seats app crashes the whole computer while I am trying to brake on the highway?
That is exactly the fear. It's called resource conflict or interference. And it is the software engineer's ultimate nightmare. In a traditional workflow, you write the code, you put it in the test car, and you drive it. And maybe, just maybe, once in 1,000 miles, the heated seats turn on at the exact same millisecond the ABS tries to kick in and the system lags for a half second.
A race condition.
Exactly. Catching that in a physical car is worse than finding a needle in a haystack because you can't always replicate it. The report details a software solution called MotionWise, which uses a deterministic schedule.
Deterministic.
It means the outcome is predetermined by mathematics, not by chance or timing. Before the software is even compiled, they use math proofs to create a master schedule that reserves specific, guaranteed slices of processor time for safety-critical functions.
Okay, I follow.
It proves, mathematically, that the brake signal will always, 100% of the time, get the processor resources it needs, no matter what Netflix or the climate control are doing in the background.
So they don't even have to test to see if it works. They know it works before they start because the math says it has to.
They still test it, of course, but the architecture is correct by design. It structurally prevents those timing violations from happening in the first place.
And the economics of catching this stuff early are staggering. The report mentions a concept called shift left.
Shift left is a big term right now. It just means moving testing earlier in the development timeline, to the left on the calendar.
Right. And there is a killer stat here in the report. The cost to fix a bug.
This is one of those numbers that every automotive CFO should have tattooed on their arm. The report states that the cost to fix a software bug during the initial coding phase, like when it's just on the developer's laptop, is 1 unit of cost.
1 unit.
If that bug slips through to the system integration phase, the cost goes up 10x. If it gets all the way to the physical prototype mule phase, it is 100x.
And if it gets to the customer?
If it gets to production and you have to issue a global recall, manually update the fleet, face the class action lawsuits, and try to repair the brain damage. The cost is 640 times higher than if you had just caught it on day one.
1/640th. When you put it that way, buying a $20 million simulator lab to catch those bugs early sounds like an absolute bargain.
It's practically a coupon. That is why the executives are finally signing off on these zero prototype labs. It is not because they suddenly love video game technology. It is because the financial risk of a massive software recall in 2026 is a literal existential threat to the company.
So looking at the big picture, who is actually winning this race? The report breaks down the global landscape into 3 main regions: Europe, North America, and Asia. And it seems like everyone has a very different flavor of how they approach this.
It's fascinating cultural anthropology, actually. Let's look at Europe first. The report calls them the purists.
The purists. I like that.
Europe, specifically Germany and Italy, with major players like VI Grade, AVL, and Porsche Engineering, is completely obsessed with NVH and handling. They care deeply about the soul of the car.
The driving feel.
Yeah.
The heritage.
Right. Brands like Volvo and Mercedes-AMG are using these massive simulators to hit that 40% prototype reduction target, but they're doing it specifically to perfect the ride quality. There's a great stat here. Ford Cologne actually finalized 75% of their EV sound design entirely in the virtual world.
So the actual sound of the new electric Explorer that was mostly decided by someone sitting in a simulator rig.
Yes, and they have incredible facilities like SimCenter Udine over in Italy, which is basically a high-fidelity virtual proving ground. It is where the art of traditional driving meets the hard science of simulation. They use these tools to ensure that even though the car is electric and run by a supercomputer, it still fundamentally feels like a Porsche or a Mercedes.
Okay, moving across the Atlantic to North America, the report calls the American strategy the scalers.
North America, mainly Ford and GM, is heavily leveraging the tech giants in their backyard. Microsoft, AWS. Their focus isn't just on handling, it's on scale, automation, and the cloud.
It's the Silicon Valley influence bleeding into Detroit.
Exactly. They are hyper-focused on DevSecOps development, security, and operations. They are using huge frameworks like Microsoft SFI to do design for security. Since American OEMs produce such massive volumes of vehicles, they need massive cloud collaboration just to manage the software updates.
Right.
They are slightly less focused on the artisanal feel of one specific suspension corner and much more focused on the robustness and security of the entire fleet's software architecture.
And then we have Asia. The report labels them the speedsters.
Asia is all about velocity. Brands like NIO, Hyundai, and suppliers like Bridgestone. Look at NIO, a major Chinese EV maker. They are setting lap records at the Nürburgring in Germany, and they are doing huge amounts of that suspension and aero setup entirely in simulation before they ever hit the track.
And Bridgestone. I mean, they make tires. How does this apply to them?
Tires are historically incredibly hard to model mathematically. They are flexible, they heat up, they wear down. But Bridgestone is using advanced virtual tire models to cut their physical tire prototypes by a massive 60%.
That is huge. That is a lot of rubber not being burned on test tracks.
And Hyundai is focusing heavily on active sound design, tuning the audio feedback virtually. But the key takeaway for the Asian market is supply chain virtualization. They are moving so incredibly fast because they are forcing all their suppliers to move fast right alongside them.
Which leads us perfectly to the final recommendations in the report. If you are an automotive engineer listening to this, or a supply chain executive, what should you actually be doing? The report has some pretty strong, almost aggressive orders here.
The first one is definitely the hardest to swallow. Mandatory virtual sign-off.
Making it the law of the land.
You have to fundamentally change the official product development process, the PDP. The report suggests a hard, unbreakable rule. You cannot cut steel for a factory mold until the virtual model is fully signed off.
No cheating.
No cheating, no exceptions. They set a very clear target. 80% of the HMI, the screens and interfaces, and 75% of the NVH must be finalized before the A-sample is ever built.
The A-sample being the first real physical prototype.
Right. If you aren't hitting those numbers virtually before you build a car, the report says you are failing the strategy.
That requires an enormous amount of corporate discipline.
It really does. The second recommendation is to build a true zero prototype lab.
Is that different from just, buying a really nice simulator?
Completely different. Don't just buy a $10 million simulator and stick it in the basement for the test drivers. You need a fully integrated lab. You need the driver-in-loop simulator right next to the NVH simulator, right next to the XR virtual cockpits.
The unified hub.
It has to be a collaboration platform. The chassis team, the electronics team, and the software team need to be in that same room together.
Breaking down the silos. Because usually mechanical chassis guys kind of hate the software guys, right?
Exactly. The chassis guys want the car to feel amazing on a back road. The software guys just want the code to be stable and not crash. You need them in the same room, driving the exact same virtual car, to realize that their problems are totally interconnected now.
The third major recommendation is for the supply chain. Model-based delivery.
This is the don't just send me a physical tire thing.
Right.
OEMs should demand that suppliers don't just put a physical part in a box and ship it.
Wow.
They must also send a high-fidelity FMU or FMI model of the part.
FMU.
Functional mock-up unit. It's a universal standard for sharing executable computer models. If I am Ford and I am buying a new steering rack from Bosch, I want the exact digital code that represents how that steering rack behaves so I can plug it into my virtual car and drive it today.
But wait, if I am Bosch, do I really want to give Ford my secret sauce? My physics code reveals exactly how my product works under the hood? If I send them the raw math, couldn't they just copy it and build it themselves?
That is the core tension of the whole supply chain right now, and the report suggests a compromise using what they call obfuscated models.
Obfuscated. Hidden.
Exactly. It's like a black box. The digital model works perfectly, the inputs go in, the highly accurate physics outputs come out, but the internal logic, the actual proprietary code, is completely encrypted or hidden.
Okay, I see.
It protects the supplier's intellectual property while still allowing the car maker to test the full system virtually.
That sounds like a very necessary compromise for the industry to function, but it also sounds a little mysterious.
It is. It creates a trust but verify relationship that is based entirely on mathematics rather than full transparency.
So let's wrap this up. Looking at everything from the hexaref hardware to the AI hunting for bugs, it is clear we are witnessing the ends of the traditional crash dummy era.
We really are. The era of the digital twin has fully arrived.
And for you, the listener, the so what here is actually pretty profound.
It means safer cars, develop faster. It means the car you buy in 2026 will have been tested over millions of virtual miles. It will have faced edge cases, massive blizzards, triple sensor failures, a child running into the street that a physical test driver could never safely replicate in real life.
The cars are basically born digital.
Born digital and raised in the cloud before they ever touched the pavement.
It is an incredible leap forward for engineering.
Yeah.
But, I want to leave us with a thought based on that obfuscated model concept you just mentioned at the end there.
Go on.
We are building these incredibly complex machines that are undeniably safer and smarter. But if the tire model is a proprietary black box, and the steering model is an encrypted black box, and the AI driver is a massive neural network that no human brain can fully read or comprehend.
I see exactly where you're going with this.
If the entire car is essentially built from encrypted digital black boxes stitched together by an algorithm, who actually understands how the whole machine works?
That is the ultimate question of the software-defined era. We are moving rapidly toward a future where the system integration works perfectly, but the system itself might just be a giant puzzle that even its own creators cannot fully see inside.
We're trading transparency for complexity and speed.
Exactly.
Are we driving the car, or is the code driving us? Something to think about next time you see a software update notification pop up on your dashboard. Thanks for joining us on this deep dive.
See you next time.